Okay, so number one, we have one term in the denominator, but this is not going to be a good fit where we can split up. Natural log and 5x are not in the same family. It's not like we can just rely on power rule if we're to split up. The next step is, well, it's got to be use substitution, but what is it? Is it going to be the x in the denominator? Is it the denominator, or is it what's inside the parentheses? Sometimes it's the parentheses, sometimes it's the denominator. I think it's a little bit of trial and error, but it's also thinking about the derivative. Whatever u value that you consider, think quickly about what the derivative could be. And if you see a variation, or if you see something that resembles your derivative elsewhere in the problem, that's a good indication that you're on the right track. If I let my u value be 5x, my derivative will be 1, and 1 is not going to help cancel that element of x out. But if my u value is natural log of x, the derivative 1 over x, at least I see something that can at least have a chance of getting to that remaining x there. Okay, so yeah. Before you go too far into the process, just think about the derivative, and that should give you a better feel for whether you're on the right track or not. Okay, so we're going to keep going here, cross multiply. Okay, I'm ready to make my substitutions, replace element of x with u, replace dx with x du. Just like what we wanted, the x's cancel out, but there is that 5 left over, so we'll pull that 5 out in front. That's 1/5. So now we're looking at power rule, right? And replace the u with x, or in terms of x. You can leave that 15 out in front, or you can put it below. Doesn't matter. Either way is fine. Okay, questions with 1? All right, number 2, we have a messy function here. If we consider maybe the denominator is a higher degree, looks like the derivative of each of these should pair up nicely with what we see in the numerator. So let's go after the denominator as our u value. And also another rule of thumb here is the messier your problem, the larger your u value has to be, right? The fact that we have to get u substitution, we have to condense our problem into something that is available, one of our rules here. So we only have a set few integral rules here. So the messier your problem is, the larger your u value will be. Okay, so I'm ready to make my substitution, replace my denominator with u, replace dx with this du. So these are not exactly alike, but we're still on the right track here. We see x cubed, x squared, x. We should be able to get these to pair up a little better, but maybe we need to go through factoring in order to get these to be more similar to each other. So I'm going to factor out the GCF of 7. I'll factor out the GCF of 4. Yeah.
So for this one, what I did is I just like crossed out all the x's and said that they canceled, and then I did like 7 plus 21 plus 7, and then I did 4 plus 12 plus 4, and I did them over each other, and I got the same.
Yeah. I mean, that may work in some situations, like in this case, but
Yeah.
I think the danger is typically we don't like to cancel across addition and subtraction, because then you're running, then it's kind of dangerous, because you don't know, sometimes it may work out, sometimes it may not. So I would think, you only want to cancel if things are being multiplied and they're nicely separated, right? So I think that's a better strategy. I think in this case it worked out, but it's not going to work every time. All right, so I'm going to factor out GCF of 7. Now, having said that, if it was, for some reason, if it was like 7x cubed times 21x squared times 7x over 4x cubed times 12x squared times 4x, then you can go at it. Then you can just, cancel anything that you see, and that's fine. But as soon as you see plus or minus, then, all bets are off.
So like for that one, would be like multiply.
Sure, yeah. Then you can do all those properties you were mentioning, and that all works. Yeah, but as soon as things are being added and subtracted, it's not as clean as you would like. Right, so after we factor out the 7 and 4 respectively, we have a much cleaner relationship, right? The parentheses are matching perfectly. They're being multiplied with something else. And so this can pair up much easier. Right, so the 7th, 4th can come out in front. And now we have a nice natural log rule. And then replace the u back in terms of x. Any questions? All right, number 3, there's a certain look of synthetic division problems, right? There's like denominator is always like a linear, and there's always 2 terms like x minus 1, x plus 2, and the numerator needs to be at least the same degree, if not higher. In this case, it is higher, but it could also work if it's the same degree. If it was like x plus 3 over x plus 2, we could go through synthetic division, but there's a certain look to it, right? So the hope with synthetic division is that we're going to separate into individual terms so that rather than dealing with a messy fraction, we're able to split up into 3 or 4 separate problems, smaller problems. So start off with that denominator. Look for your factor there. So set equal to 0. You're always going to take the opposite sign of what you see in the denominator. And then just put numbers down, numbers that represent each of your degrees. 1 is for x to the 4th, 3 is for x cubed, -1 is for x squared. Now, there is no representation for x, so we need to have a placeholder for that x to the 1st power. We'll use 0 and then -5. Drop the first number down below the line. Multiply. Add. Multiply. And add. Multiply. Multiply. We started with x to the 4th. Just understand that once we're below the line, we're going to be 1 degree lower than where we started. So this is now going to be at x cubed. This is now x squared. This is now x. This is the constant. And then finally, because there's a number left over, that's going to be your remainder. We're not going to stop here. All we've done is we've made this into an easier problem because now we just have 4 power rule problems, terms, and then there's a natural log u substitution at the end. There's a little bit of use substitution going on here, but it's easy enough where you can jump directly from here to here without having to go through a full use substitution steps. All right, everybody good? Everybody good with 3? 4? Okay, too many terms in the denominator. We can't split up into individual fractions. So we're looking at use substitution. We want to let the u value potentially be this parentheses because we know that 1 plus root x is going to produce some leftover x because that x is inside a radical, right? And so we need to have something as our u value and save something for the derivative. Right? So we're going to let this be our u value and let this root x hang out here and hope that the derivative will match and pair up with that leftover term. And remember, bounds is not going to play a role until after we're done with pretty much the entire problem. I'm going to get that square root of x ready for power rule. Okay, so now du over dx. 1 goes away. X to the 1/2 becomes 1/2 x to the negative 1/2. I'm going to do some cleanup there before I cross multiply. So I'm going to make that x come down to the denominator, make it a positive exponent. It's being a little bit, feels like it's a little bit cleaner to work with positive exponents than negative exponents. Now I'm going to cross multiply, solve for dx. Make my substitutions. I'm going to convert that x to the 1/2 back to root x just to see that they're the same. There's a leftover 2 out in front. One over u to the first power, that's natural log. Instead of plus c, we're working towards our bounds. So let's bring our x's back. Now upper bound first. Then a lower bound. This is fine. I saw on the previous test where students got to this point and they would put a plus C at the end. Remember, you're only doing plus C if you have indefinite interval. If there are no bounds, then you can make sure you have that plus C, but there's no plus C if there's bounds. The C's will just end up canceling out. We're going to get a specific value. There's not going to be any general portion of the problem anymore. It's just should get down to a specific numeric value. Okay, the 3x and 4x tells us we have to go through u substitution. Right? It's not just x. There's definitely some left over. I will go through the full u substitution process, but can we predict what's going to come out of this 3x? It's gonna be the reciprocal. It's gonna be 1/3. What's gonna happen with that 4x? 1/4. Now, if you don't feel comfortable memorizing that relationship, don't worry about it. Just go through your full u substitution process. I don't want you to feel like you have to go through that shortcut if you don't want to. So, but if you are comfortable with that, you can jump directly to that without having to go through your full u substitution if you know what's going to come out of it. And so there's two different u values here, two separate problems here. So u equals 3x, du over dx equals 3, 3 dx equals du, dx equals du over 3. And so we replace dx with du over 3. So notice the 3x is now turned to the denominator. So basically a 1/3 is going to come out of it. We still have to keep track of that too, but basically there's a 1/3 that's resulting from that 3x through u substitution. So from here, we can apply the new natural log rule that we've been going through. When I think of cotangent, I think cosine over sine. And I know that it's going to be sine that's going to show up. So 2/3 natural log absolute value of sine of u. And then I don't see any C letter in between my absolute values. So I know that this is going to be a positive natural log. Okay, so that's only half the problem, right? We still have to worry about the other part involving secant. Here, if you can predict what's going to come out of it, it's going to be 1/4. as a result of u substitution, but I'll go through the steps. Question. Secant, when I think of secant and tangent because of the derivative rule. And so that's those two trig functions will show up, but it's going to be within natural log, and there's going to be a plus between the secant and tangent. I don't see any, oh, sorry, there is a C there, but there is no C as the first letters within my expression here. So there's not going to be a negative in front. So this will be a positive. Well, there's already a negative. I'm not going to change the sign there. So here's my final result. And then bring back all your x variable. Any questions with 5? Number 6, I think the paper kind of cut off that exponent a little bit. It should read 2 over x, 7 to the 2 over x, all over x squared. So this looks like it could be an a to the u rule. So if we want to target a to the u rule, then that means we're looking at the exponent as our u value. So we need the entire exponent to be the u value, the 2 over x. And then we're hoping that this derivative will take care of this x squared down the road. Now 2 over x, it looks like quotient rule, but we prefer to avoid quotient rule if possible. So I'm going to bring that x up to the top so I can just rely on power rule for this derivative. The negative 2x to the negative 2. Let me do some cleanup before I cross multiply. I prefer to work with positive exponents if possible. So I'm going to bring that x back down. Okay, now I can cross multiply. I'll replace 2 over x in terms of u. Keep the x squared, replace dx with x squared du over negative 2. X squared goes away. Careful that you don't merge these and make it negative 7 over 2. Remember, this is the negative 1/2. It's not compatible with this 7. This 7 is not just a 7, the 7 raised to the u, so this is going to be its own thing. So make sure you keep these completely separate. Okay, so then our rule is integral of a to the u is 1 over natural log of a times a to the u plus c. And don't forget to bring back your x. Let me do one more. If you guys can find another sheet of paper, let me have us try this one here.
Wait, yeah, isn't it supposed to be dx or something?
Oh, sorry. Yeah, you're right. My bad. Sorry, dx. Got my letters mixed up. Okay, too many terms in the denominator, right? We can't split this up into individual fractions. We have to think about u substitution. What could be our u value?
E to 3.
Yeah. Okay, so e to the u's derivative is e to the u times u prime. Let's multiply. Okay, e to the 3x above Denominator is u cubed. du over 3 e to the 3x. That's a good sign. We should be able to get that e to the 3x's to cancel out. Everything cancels out nicely. We're in terms of u. Okay, what rule do we use here?
Well,
Is it natural log? Not.
what I did is I did like u to the -3.
No.
And then I did like u to the -2.
Power rules, yeah. So I purposely did, I made a change to that exponent because I want us to make sure that we understand there's a certain time when we use natural log and there are other times when we don't, right? If it's any other power other than 1, you have to bring it up and go through a power rule. We cannot adapt this into natural log, even though it feels easier because it's just one step and done. But here you got to bring it up, make u to -3, and then go through power rule. Right, so just be careful, right? Don't assume that every u in the denominator is going to be natural log. This is a power rule problem. Okay, replace the u back in terms of x. Hey, if you haven't had a chance to do it, I think it's good practice to go through your rules. Make sure you know all your derivative and integral rules on this sheet. Let me know if you have any individual questions. I have a handout for these rules there if you didn't get a chance to pick one up. Hi, thank you.
Ready? Wait. Yeah, but she has to clear them off.
It's like these two right here. So when I'm solving for like when I'm doing U substitution, like I know that's U substitution.
Yeah.
But I think I'm just having a small problem of like which one do I choose?
Right.
I looked at the key
Typically,
and said
yeah. Typically, it's the denominator.
okay.
And also typically it's the expression that's more complicated potentially. So now, as I say that, that's not always the case, but in this case, it is a denominator because we just saw with number 1 during our help session. Yeah, this ends up being the numerator.
Yeah.
And so
But it's in parentheses.
It's in parentheses, true. And then also another thing is that you want to think about what the derivative is. If you can
Mhm.
imagine the derivative showing up elsewhere in the problem,
Okay.
then that's usually a good sign. So yeah, so that indicates, okay, natural log of x is 1 over x. I see an x left over there. But in a problem like this, yeah, if you don't see any parentheses, typically it's the denominator
Okay.
because it's easier for the numerator to cancel out.
It would be the whole denominator in this
It'd be the whole
case,
denominator.
and then, like, I know this one was weird. 'Cause
Yeah,
it's,
this one's
like,
weird.
divided
Yeah,
out.
this one's weird
My
because we can see a little bit of that a to the u,
Mhm.
but
It's
that a is in the wrong spot. So we actually have to rewrite the problem and make it 2 to the negative sign of x
Yeah,
in order to get that a to be in the right spot. And then this is your new value.
okay.
Yeah, so that's.
Yeah, I got it once. I solved it I solved it the wrong way. I kept in the denominator and then I took the key and like it made sense.
Yeah.
I was just really confused on this one because I was looking at another problem. I was just making sure like when to use substitution and when not, or, like what. Like this one's in the power, so you can use that. But there was another one where, and this one's in the parentheses.
Yeah. So I don't know if this helps, but another thing that I do when I think about use substitution is I'm trying to look ahead. I'm trying to look ahead to see, okay, what could this end up looking like, right? Because if that's the u value, then that should hopefully work towards this this 1 over u rule.
Yeah.
But if this is the u value, then yeah, I know it's kind of hard because then you're thinking, well, maybe this could be u substitution
Mhm.
with that being the u value. But when everything is equal like this and no parentheses, usually it's the denominator.
Okay, perfect. Because I was just trying to make sure that like, because even this one, like it's the exponent and it's
It's the
like not been a to the u, and that's what you're trying to make it. So I'm just trying to find like a pattern of when I need to use the like the exponent or the denominator. Because my first instinct was to use this, but then it was like this could be an a to the u.
Yeah, but if you see an exponent, a messiness in an
Mhm.
exponent, it's typically going to have to be a to the u. Otherwise, it's really hard to get anything in the
Yeah.
exponent to cancel out. So
Thank you.
For Troy on the quiz,
Yeah.
is it just gonna be like these ones that we need to focus on? Or
Yes.
should we like keep in mind when?
keep this in mind. Yeah, because these derivative rules, we need to make sure that we should always know.
Okay,
These are the new ones that we're adding.
but like if it, so like say on the quiz, it's like derivative of like secant, should I be like focusing on
No,
this?
no, no,
one?
this one here. This is the integral. There is no integral of secant here, so it's going to come out here.
Okay.
Right.
That's where should I?
You can, oh yeah, if I can see that. Yeah, okay. I'm gonna have you select.
I don't know if she's.
Yeah.